Okay, so the last couple of weeks we've been talking about water as a molecule and the properties of water. We need that background because in about a week or so we're going to start looking at how water moves on the surface of the earth into the subsurface, and then how it moves through rocks and soils and pore spaces beneath the surface. So what I'm trying to do with these first couple classes is give you all the background that you need to kind of understand where we're going with this and how things actually do move beneath the surface and why they move the way they do. So last class we went through some different processes and properties of water. And today what we're going to do is spend some time talking about one that is going to be something that comes up again and again and again in this class. Probably the single most important concept we're going to talk about, because it dictates how water moves in the subsurface. When we look at things like the water table and pumping, this will have a huge effect, and you're going to do lots of little calculations with this stuff. Now, if you've had me before, you've actually seen some of this. So I teach this in most of my classes because it's really one of the fundamental concepts in why geologic things move on the surface of the earth. So let me put this up. So we talked about 4 properties last week, and this 5th one is what we're going to spend most of our time with today. And like I said, you're going to see this again and again and again. So if you have any problems today as I'm going through this, stop me, ask your questions, make sure you have an understanding of what we're doing here. So one thing water can do, which is really important for groundwater systems, is that it is capable of forming what we call hydrostatic pressure. If you had me for ESCI 200, we talked about this. If you had me for volcanology, we talked about magmastatic pressure. We talk about pressure a lot in my classes. So first, some background. We're going to start with the basics here. We're going to come at this kind of from a physics perspective. What is a force? You guys remember forces from my class or from physics classes? It's really hard to put into words, isn't it? It's actually much easier just to kind of throw out the physics equation, which is?
Mass times acceleration.
Force is a mass that is accelerating. Mass times acceleration. Units are obviously important because we're going to be calculating things in this class. What do we use for a unit for mass? There are several, but a common one. Grams or kilograms. For here in groundwater, we're mostly going to be talking about big things, big bodies of water. So we're going to be talking about kilograms. I'll digress a little. What's the difference between mass and weight?
Weight has a gravity component to it.
Perfect. Weight has a gravity component. So I'm about 70 kilograms. That's my mass. That's how much stuff makes up Steve Anderson, is about 70 kilograms of material. Here on Earth, that 70 kilograms weighs how much?
2.2.
70 times 2.2 is 154 pounds. A little more than that. Okay, not a lot more. A little more than that. Okay? Now, if I was on Mars, all right, I would still have the same amount of stuff, right? I don't change if I somehow get transported to Mars. I still have 70 kilograms of material, okay? But on Mars, the gravity is much, much less. And I'm going to weigh about somewhere between 30 and 40 pounds on Mars, okay? So weight has a gravitational component. Mass doesn't change wherever you are. It's just the amount of stuff in a system, okay? So we measure mass in kilograms. What about acceleration? What's the unit for acceleration? What does it mean to accelerate, first of all? If I'm accelerating, what's happening? Think of your car. If you accelerate in your car, what's really going on? You're changing your velocity. So let's go to velocity. Velocity, similar to speed, except velocity has a direction with it. So how would we, what sort of units do we use to measure velocity? In a car, what do we use? Miles per hour, right? Miles is a distance per time, right? Usually in science, we tend to stick to the metric system, so we'll use something like meters per second, right? So acceleration is we're changing our speed. Let's say we go from 5 meters per second to 10 meters per second. That's acceleration, right? But you could go from 5 meters a second to 10 meters a second over a very long time period. We're just sort of slowly speeding up. If you've ever been sitting at a stoplight, somebody poking in front of you, they barely get going, they barely accelerate. I like to accelerate really fast, okay? I like to get up to speed. So because I accelerate quicker, it takes me less time. Now, if I went from 5 meters per second to 10 meters per second in 1 second, what's my acceleration? I started at 5 meters per second, right? I ended at 10 meters per second a second later. You said it was a change in velocity, right? What's my change in velocity? 5 meters per second, but I did it in a second, right? So our unit for acceleration is meters per second every second. And that turns out to be meters per second squared. So you can think about it as meters per second per second. Kind of a weird term, but you'll get used to it. Now here on Earth, if I drop something from way up in the sky, gravity has a set rate here on Earth. It's 9.8. You might as well know that now because you're going to use it all semester. The acceleration due to gravity on Earth is 9.8 meters per second every second, meters per second squared. So that's the acceleration due to gravity on Earth. 9.8 meters per second, or 9.8 meters per second squared. So let's go back to our definition for force, right here. What is our unit of force? We know force equals mass times acceleration. We measure mass in kilograms. We measure acceleration in meters per second squared. This unit right here, kilogram meter per second squared, is something that we call a Newton. It's a basic measurement or a basic unit of force. A kilogram times meter over second squared is a Newton. That is our unit of force. Okay, any questions on that? All right, I'm going to flip the slide here. Let me just put up that last little equation. Okay, force equals mass times acceleration. Force so equals ma. And if we use those units again, we measure mass in kilograms, acceleration in meters per second squared, and that's the same thing as a Newton. Okay, so we know force. So what is pressure? Pressure is also known as stress. How is pressure different from force? Think of it this way. Okay, I'm 70-ish kilograms, right? Is gravity pulling me down? Definitely. So if I'm standing here, gravity's pulling me down. If you put your hand under my feet, would you feel some pressure? Okay? But I have fairly good size shoes on right now. I have size 11 feet. What if my feet were only about a centimeter square and I stepped on your hand? Or the example I always use is, what if I was wearing a high heel and stepped on your hand with the heel? Going to be a lot of stress under that, right? A lot of pressure. What's different about those examples? My big shoe versus the high heel. Surface area. Yeah, so pressure is actually a force applied over a surface. So we tend to use this little sigma to denote stress or pressure. And it equals force over an area. Remember, our unit for force was what? It was the Newton. Okay, so I'm going to put up the unit for newtons, kilogram per meter over second squared. That's our force. What unit do we use for area?
Meters squared.
In this case, we'd probably use meters squared just to keep the units consistent. So there we go. All right, let's go back to our basic algebra. Can we reduce this term in any way? We have a meter on top, right? We have meter squared on the bottom. We can cancel out that, and we end up with something that actually looks really similar to a Newton, but a little different. The unit is kilograms over meter second squared. So again, compare these two units right here. This top one is a unit of force, kilograms times meter over second squared. This bottom one is a unit of stress, it's kilograms over meter second squared. Looks similar, but the meters are, one's in the numerator and one's in the denominator. Okay? This unit right here is something called a Pascal. And it is our typical unit for stress or pressure. So we measure force in newtons. We measure stress in pascals. Pascal is simply a force divided by an area. Okay? So keep, I'll use a different color here. Keep these two units in mind. We're going to use them a lot this semester. They look really similar, but clearly they're different, right? Okay, so what does this have to do with hydrostatic pressure? Okay, let's take a look at that. Any questions before I move on? All right. What is hydrostatic pressure? You might get slightly different definitions depending on whether you talk to a physicist or an engineer or a geologist, but I'm just going to put up a pretty simple one here, and it works for this class, is that it is the pressure exerted at the base of a water column. Are you guys under some pressure right now?
Yeah.
From what?
The atmosphere.
Atmosphere. And what do we call, what's another name for atmospheric pressure? Sometimes called barometric pressure, right? That is the atmosphere being pulled down by gravity on top of you. It's actually pretty considerable. You guys don't notice because we're used to it all day, right? You might get a slight change in atmospheric pressure as weather systems move in, or the one that's probably the easiest to understand is that if you drive up into the mountains, go up to 10,000 feet over some of the passes here, your ears start popping because there's less pressure because you're higher up in the atmosphere column and there's less atmosphere above you that's being pulled down, okay? Hydrostatic pressure you probably have some experience with too if you've ever been swimming and diving. If you dive down more than a few feet, what do you feel? Where do you feel it? In your ears, right? Yeah, that's that water that's actually putting pressure on your ears. If you go to the base of the oceans, the hydrostatic pressure is more than considerable. It's crushing. We talk about magmastatic pressure in volcanology. If you had me for that class, that is the pressure at the base of a magma column. We also have lithostatic pressure, which is, what does lithos mean?
Like
Rock. So it's the pressure of being buried under rock. So the deeper you go into the earth, the more lithostatic pressure you have. The more rock that's above you that's being pulled down on top of you. Okay, so hydrostatic pressure is the pressure at the base of a water column. Lithostatic pressure, base of a rock column. Magmastatic pressure, base of a magma column. Barometric pressure, base of an atmospheric column. So think about this in terms of being buried, okay? So what factors affect the pressure of being buried? You can be buried under lots of things, right? The pressure comes from gravity pulling down stuff on top of you. Okay, so if you wanted to create a lot of pressure, tell me what you would do. A lot of pressure due to burying. If I wanted to put you under a lot of pressure by burying you, what would I do?
Have a lot of that stuff.
A lot of stuff on top of you, right? So first thing is, let's just draw pictures of my backyard. I'm going to dig a hole. I'm going to put you in the hole. I'm going to bury you. Okay? If I really want to squish you, what do I do with this little diagram here? How do I put the most pressure on you?
Get something real heavy.
Okay, so the stuff that I'm going to bury you with has to be heavy, right? Another word for that is dense. If the stuff above you was styrofoam popcorn, okay, that's not going to put you under much pressure, right? But if it was ball bearings, yeah, it's going to be a lot of pressure, right? Somebody sort of said it already, but the deeper I bury you, the more pressure you're going to feel, right? And again, this is a pressure from being buried, from stuff being pulled down, right? What's doing the pulling down? What's responsible for pulling stuff down on top of you? Gravity. And gravity here on Earth doesn't change much. But it can if we go to other planets or other systems. So the third factor is gravity, which we'll go with that arrow. So depth, what units do we use to measure depth? Meters is a good one to use. What about density? What is density?
Oh, mass over volume.
It's how much mass you can pack into a space, right? So it is mass, which we measure in kilograms, over a volume, which we will, in this case, use meters cubed. Gravity, we measure the acceleration due to gravity. What is acceleration? Units?
Meters per second squared.
Meters per second squared. If you multiply those three factors together, depth times density times gravity, what unit do you get?
Looks like a Pascal.
Yeah.
What unit is the result? You guys are saying when you do this, you get a Pascal. Does that make sense? It should be a pressure term, right? What is Pascal? Or unit of pressure. So I'm going to put this on the next page here. So remember depth in meters times density in kilograms per meter cubed times gravity, meters per second squared, meters times kilogram per meter cubed times meters per second squared. Can we cancel some stuff out? Got 1 meter on top, 2 meters on top, meter cubed on the bottom. So we can get rid of 2 of those. We are therefore left with, doesn't look like anything else cancels out. We have a kilogram on the top. Looks like we still have 1 meter in the denominator. We have second squared in the denominators. And that equals a Pascal, which is a unit of pressure. Okay, so some things you should know, okay? So one thing I want you to know is that gravity here on Earth is 9.8 meters per second squared. You're scientists, you need to know this. It just needs to be part of your working vocabulary. Learn it, memorize it. I think most of you have it already, okay? Now you're also geologists. So there's a few things about geology you should have sort of stored in your working memory. And these have to do with density. So let me get rid of that. That is not the right term. Let's see. The density of water, okay? So we're going to use, that is not the right term. Density of water. And this is fresh water. It's a nice convenient term. It's 1,000 kilograms per meter cubed. Salt water is about 1,003.5. So if you dissolve stuff in, the density goes up a little bit. But for fresh water, and that's what we're going to deal with mostly in this class, I want you to know that it's 1,000 kilograms per cubic meter in its density. It's also worthwhile to know that sedimentary rocks are on the order of twice as heavy, somewhere around 2,000 kilograms per meter cubed. In groundwater studies, most of the time we're dealing with sedimentary rocks because they make good aquifers. So that is a density that you really should probably know as well. But it's just basically twice of what water is. It varies a little bit, sandstones and shales and all the different sedimentary rocks. Some are around 2,000, some are around 2,200, but this is kind of a good ballpark guesstimate, okay? Igneous and metamorphic rocks are around 2,500 kilograms per meter cubed. Now, you don't need to know this one, but one of the densest things that we have in all of our science is gold. That's how we gold pan, because it's so dense. Gold is 19 times the density of water. So it's 19,000 kilograms. Pretty impressive. Gold is really heavy. If you had a gallon jug full of gold, a gallon jug of water weighs about how much? Do you guys know? It's about 8 to 10 pounds. Let's just use 10 pounds. Gold is 19 times heavier. That gallon jug of gold would weigh almost 200 pounds. You'd have a tough time just sort of picking it up and bringing it home. So, yeah, densities vary a lot with earth materials. But these are the values that I really want you to kind of have at your disposal in this class. Okay, so I'm going to give you a problem. All right, let's go on to the next page. Any questions here? All right. Here is a question for you. What is the hydrostatic pressure at the bottom of a 0.3 kilometer deep lake on Mars. Okay, so our pressure, hydrostatic pressure, equals what? Equals depth times density times gravity. What do you know? You know depth, and you should know density, right? What don't you know? Don't know gravity. So gravity on Mars is about 3.3 meters per second squared. So it's about a third of what it is here on Earth. Okay, so take a second and calculate. Okay, so the first thing that hopefully you noticed was our depth term isn't in meters, right? So we need to change that to meters so that the units come out right in the end. So if we take 0.3 kilometers and turn it into meters, how many meters is that going to be? 300. So 300 meters times 1,000 kilograms per meter cubed times 3.3 meters per second squared. We can cross out some units. We have meters, we have meters. We have meters cubed on the bottom. Would you guys end up with an answer?
990.
So if you 300 times 1,000 times 3.3
Oh, oops.
should be 9.9 times 10 to the 5th. What's our unit? We have a kilogram on top, meter still on the bottom, second squared still on the bottom. which is also a Pascal. Now, if you were buried under sedimentary rock instead, what would this value be? What's the only thing that's going to change? Density. And the density of sedimentary rock is how much more than water? Doubled, right? So basically you just multiply this by 2 and you'd end up with 1.98 times 10 to the 6 pascals. So if you're not following it, take a look at it. We're going to do a lot more of these, okay? Lots of these. When we talk about groundwater, this is what makes groundwater move, is pressure. Okay, so we're going to be calculating pressure all the time in here. That's what makes groundwater flow. Response to pressure. So make sure you have this material kind of well understood as we move on. Okay, any questions? All right, let's just finish up with a few final properties of water. One thing that water does that's kind of interesting is it has what we call capillarity. It's the ability of a liquid to move by cohesion along a solid. So let's say we have a solid here, and this is the surface of the solid right there. Now, depending on what your solid is, could be wood, could be paper, plastic. All of those materials are made of atoms that are bonded together. And anytime we have atoms bonded together, we have the potential to form dipoles on there. And some solids have lots of dipoles. They have little positive and negative charges on their surface. And if we have a body of water right here, remember, in that body of water, we have water molecules that have slight positive charges, slight positive dipoles on the hydrogen, and slight negative dipoles on the oxygen. And what can happen is the little attractions on the solid will attract the dipoles on the water, and the water will actually cling to these and start to climb up as the different parts of the water molecule feel the charges on the surface. And that's called cohesion. You may have heard of the term adhesion, and that's when you have something sticking to itself. So water molecules sort of sticking together would be adhesion. So again, this is one of the results of the interactions of dipoles that you have on these water molecules. Now, if you don't want capillary action, what you can do is you can try to get rid of these charges on the surface of the solid. One way to do that would be to put an oil or something on it, coat it with something that doesn't have strong dipoles, and then water won't feel it as much as they'll feel the other water molecules nearby. Okay. Another thing about water is that its density changes in a very unique way when you go from a solid to a liquid and from a liquid back to a solid. So the density changes from a liquid to a solid are considerable. Most substances, when you freeze them, get more dense. The atomic movement slows down, they pack together tighter. But with water, it's different. Water, when you freeze it, actually is less dense. Not many substances do that, and it's because of those 105-degree angles, the water cannot form a nice stable geometry. So in fact, ice is about 91.7% as dense as liquid water. Or the density drops by about 10% when you freeze it. That's why ice forms on top of water bodies. If it was any other substance, ice would form at the bottom of the water bodies. And again, remember the water molecules have a 105-degree angle between the bonded atoms. And the result is so if you had a 90-degree angle, it would be real easy to make box shapes like rectangular prisms. If you had a 120-degree angle, it would be really easy to make things like hexagons. With 105-degree angle, it's right in the middle between those two geometries. And it tries to make both, but it does a really crappy job of both. So it can't form a good stable geometry, and it has this big open geometry which takes up more space. The other thing you should probably know, this is just a factoid, water is densest at 4 degrees C. So as you cool off water, it gets denser and denser, down to about 4 degrees C, somewhere around 40 degrees Fahrenheit. And then as it approaches the freezing point, it starts to try to put together some sort of stable geometry and can't. So it starts to expand again. But if you go to like the bottom of a deep, deep reservoir, go to the very bottom, that water is going to be about 4 degrees. You might have colder water on top of it. You might have warmer water on top of it. But the densest will be at 4 degrees right at the bottom. Okay, the very last thing we're going to talk about, and I've covered this in my other classes, so most of you have seen this, and if not, it might be new to you. Water has some really unique energy requirements. To heat it up and to change its state. So I know you've all seen the term calorie. calorie is a unit of energy. And its definition is actually the amount of energy needed to raise the temperature of 1 gram of water by 1 degree C. We sometimes refer to that value as the specific heat of water. And it equals 1 calorie per 1 gram of water per degree C. So that's how you would write that out. So if you have a gram of water, that's at 2 degrees C, and you want to raise it to 3 degrees C, you have to add 1 calorie of heat. If you want to raise it 10 degrees, you have to add 10 calories. Great thing about water is that it has these really nice units. Its density is 1,000 kilograms per meter cubed. Its specific heat is 1 calorie per gram per degree C. 1 gram equals 1 centimeter cubed equals 1 milliliter. We have all these great ways of converting water really without a calculator. So a lot of people think groundwater is really hard mathematically, but luckily from the water side of it, the properties of water make the math a lot easier than it might be. Now, you guys probably know about calories from food, right? Everybody knows food calories, right? It's a little different than a physics calorie. It's actually something we call a kilocal. So again, just a little factoid. Don't have to remember it if you don't want to. All right, so what I want to spend the last 5 minutes or so of class going through is what it takes to heat water up. Okay? So let's start with an example. We're going to try to keep this pretty easy. So we're going to start with 1 gram of water. At minus 20 degrees C. Now we're going to heat it up. I want to heat our water up. I want to heat our water up a lot so that it goes through several phase changes. What state of matter is our water in right now? Solid, right? Water freezes on Earth's surface at 0 degrees. We're at minus 20. Pretty damn cold, okay? So we have a little tiny block of ice, okay? Little tiny chunk of ice. Okay, so let's raise the temperature from minus 20 to 0 degrees C. How much heat do we need for that to happen? With 1 gram of water, how many degrees are we changing? 20. How many calories do we need? 20. So we need 20 calories. What do I have now? Tell me what I have and what's its temperature. First of all, what's its temperature? 0. And we know what happens at 0. That's the melting, freezing point of water, right? So we just took ice from -20 and we raised it 20 degrees, okay? At this point in time, what we have is ice, a solid, at 0 degrees C. But we know at 0 degrees C, if we're raising the temperature of ice, this is where ice melts, right? Melting is a process, though, that requires energy. We have to break the bonds that are holding the molecules together in ice. As it turns out, to break bonds requires a lot more energy. So just to break the bonds, so we have to break the bonds that make ice a solid at 0 degrees C and create liquid at 0 degrees C. That extra energy that's needed to break the bonds is something that we call latent heat of fusion. It varies from substance to substance. It's different for CO2 than it is for nitrogen, than it is for carbon monoxide, than it is for water. Latent heat of fusion for water is 80 calories per gram. So let's look at where we are. We started at -20, right? Every calorie we added changed the temperature of that gram of ice by a degree. So once we put in 20 calories, that ice at -20 went to ice at 0. But now we have to change phase. We have to break all those bonds, and that takes a lot of energy. And in fact, it takes 80 calories just to break the bonds. You're not even going to change the temperature. All you're doing is breaking the bonds. So what we have now, we have liquid water at 0 degrees C. So how many calories have we added so far, total? 100, right? 20 to go from -20 to 0. And then 80 just to keep it at 0, but break the bonds that change it from a solid to a liquid. Okay? Yeah?
So if you're adding heat in between, so like you've already put it up to 0 degrees Celsius and you're adding energy, it's just not 80 calories yet. It's not going to change the temperature of the ice at all?
No, and they used to do this in physics, where what you would do is you'd put ice on a pan or something and turn up the heat, okay? And what'll happen is, if you watch it, the temperature rises of the ice, but then as it actually melts, the temperature stays right at 0 until all the ice is melted. Because it's going to absorb that energy for breaking bonds rather than heat up the rest of the stuff that's there. So, all right, so let's go on. We'll come back to this. So like we said, now we have 1 gram of water, liquid, at 0 degrees C. All right, what happens if we add 100 calories? What are we going to have? liquid water at 100 degrees, okay? What happens at 100 degrees with water? It boils, right? But boiling is another change of state that requires bonds to be broken. So now we must break bonds holding the liquid together. And that is called the latent heat of vaporization. And it's a ridiculous number compared to everything else we've been talking. It's actually 540 calories per gram. You guys have all boiled water, right? It's a terribly slow process. The water gets hot fast, but then it seems like it takes forever for that stuff to actually boil. Well, it does take forever for it to boil because you have to add in such a ridiculous amount of heat to actually break the bonds holding the liquid together. Okay, so how many calories have we consumed going from ice at minus 20 to now vapor at 100? Okay, so just the change in temperature was 120 degrees, right? Minus 20 to 100. So we need 120 calories for that. But then we had to add in 80 calories for the latent heat of fusion. So that brings us up to 200. And then we had to add 540 to break the bonds in the liquid to make it into vapor. So we're looking at 740 calories. 620 was to change phase, and 120 was to raise the temperature. So you can see that it takes a lot more energy to break those bonds than to just make water rise in its temperature. So now we have steam at 100 degrees C. Raise the steam from 100 degrees C to 200 degrees C would require what? How many more calories?
Still just 100.
Just 100. So it requires another 100 calories. So let's sort of put all this together. Raise the temp from minus 20 degrees C ice to 200 degrees C steam requires, we need 20 calories to go from minus 20 to 0. We need 80 calories to go from 0 to 0, but change from a solid to liquid. We then need 100 to raise the temperature of liquid water from 0 to 100. We then need 540 calories to go from liquid at 100 to steam at 100. And then a final 100 calories to go from steam at 100 to steam at 200, which gives us a grand total of 840 calories. We raise the temperature 220 calories. So those 220 calories were to simply change the temperature. From minus 20 to 200. And then we had 620 calories to change the two phases. We're going to start with this next week. Go through it again. I'll put up a little graph that shows this as well, and we'll talk about some ways that water behaves as it goes through this little cycle. But we'll leave that here for now. Take a few minute break. For those of you that want to do your next quiz, we'll start in quarter after or so. For those of you who passed and want to bail, you can do so, or you can stay and take the quiz. Actually, I'll just put the quiz up here, and you can start at your leisure. How about that? Okay, let's